So today we start the good stuff. This is the introduction to Taylor polynomials and Taylor series, and we start with a way to approximate functions with polynomials. So this video series will probably go into multiple ones because there's a lot of material to be covered in here. The best way I know to do this is to start with what you knew about a geometric series, right? A geometric series, let's say I started with this series, the sum from n equals 0 to infinity of 1/2 to the n. All right, what does that look like? That looks like 1/2 to the 0 power, which is 1, and then 1/2 to the first power, and then 1/2 to the second power, and I'm going to keep adding and adding and adding. So I'm going to throw an extra 1 before here, right? 1 times 1/2, 1 times 1/2 squared. The next one would be 1 times 1/2 to the third, and I can keep going from there. Really, I could think of this first term here as 1 times 1/2 to the 0. Think of this as 1 times 1/2 to the first. So in general, this is a geometric series that looks like this. The sum of all the a, where a is the first term, times r to the n. All right, what do those things look like? They look like a. I could write a times r to the 0 power. I probably really don't need to. This will be a times r to the first. This will be a times r to the second. This will be a times r to the third, and so forth. Now, I know that this series converges if the absolute value of r is less than 1. So that ratio of 1/2 is good, right? We know this series will converge. We can use the a over 1 minus r formula to find out what it converges to. If it converges, then it converges to, like we said, a over 1 minus r. All right, let's take this idea and kick it up a level. And that is, I'm going to come along here and I'm going to replace all my r's with x's. And I'm going to let a equal 1. All right, so now using this formula up here, what do I end up with? I end up with 1 plus 1 times x plus 1 times x squared plus 1 times x to the third plus 1 times x to the fourth. And this keeps going. Now, I know that if the absolute value of x is less than 1, then this actually converges. All right, what does it converge to? This is important. What it converges to is a over 1 minus r. So in our case, a is 1 and r is x, so I get 1 over 1 minus x. So I claim this strange-looking statement is true, that 1 over 1 minus x is equal to 1 plus x squared plus x to the third plus x to the fourth, and so forth. Now, at first, this seems bizarre, right? 1 over 1 minus x is a rational function. You divide by a 1 minus x, so the function doesn't even exist at x equals 1, right? 1 minus 1 is 0, and now that's undefined. The other side over here is a polynomial, right? Remember, a polynomial is x to a power. So I've got 1 plus x squared plus x to the third plus x to the fourth. And even that looks funny because you're used to starting with the highest term and going down. But there is no highest term, right? It's an infinite series, so it just keeps going and going and going. So this thing here has a name. We call this a power series. All right? And this power series can be represented as the sum from n equals 0 to infinity of x to the n. So x to the 0 is 1, x to the first, x to the second, x to the third, x to the fourth. Now, when we had talked about series before, we had talked about this in terms of partial sums. And do the partial sums, if I look at a sequence of partial sums, do they converge? So let's look at what the partial sums are. I'm going to skip the first partial sum because the first partial sum is just 1, right? S of 0 is 1. So let's look at the first partial sum, S sub 1. That would be 1 plus x. 1 plus x is linear. The second partial sum, then, would be 1 plus x squared. The third partial sum would be 1 plus x squared plus x to the third. So the first partial sum is linear. The second partial sum is quadratic. The third partial sum is cubic. And then we can go on, right? The fourth one will be quartic and quintic, and then we run out of commonly used words. Here's what's important about this. Suppose I were to take this and try to graph it. So let me switch windows here. And I want to do a little bit of graphing. You're going to miss a little bit of my y equals, but I think that's okay. You'll get the idea. So my first partial sum, we said, was y equals 1 plus x. Okay, so if I graph y equals 1 plus x, I get this nice oblique line that runs to the origin. All right, let's try another one. The next partial sum we said was y equals 1 plus x squared. Okay, there's my second partial sum. The graphs look very different from each other. Let's try the third one. Y equals 1 plus x to the second plus x to the third. Okay. One more. What if I graph y equals 1 plus x to the second plus x to the third plus x to the fourth? All right, you can start to see that there's a place where all these graphs are coming together, and then outside of that window, they're all very far apart from each other. Let me do one other thing. Let me come down here and graph y equals 1 over 1 minus x. Because my claim is that there's somewhere where these graphs are similar. Now, if you look at the graph, you can see there's also a lot of places where they're not very similar. Specifically, anything to the right of x equals 1 is not going to look anything like that graph. So let me zoom in a little bit. We can get an idea of what these things look like. If I move over just a little bit, you should be able to see there you go, color coding. Color coding is a little bit important here because you notice that the red one is a linear one, the blue one is the quadratic one, the green one is the cubic one, and they all go in very different directions, especially down here in the second and third quadrant. But there's a spot between about -1 and +1 on the x's where these things overlap each other very well. And you can see that the more terms I add, right, that purple function is pretty close to 1 over 1 minus x. 1 over 1 minus x is the black function, right, between -1, and it never quite makes it all the way to 1 because there's an asymptote there. But the more terms I add to this series, the more that graph begins to approximate 1 over 1 minus x. So we have a name for that. We talk about where it converges. So where do these series converge to 1 over 1 minus x? It's a little bit hard to see because I only have a fourth degree polynomial, but if I keep adding more and more terms, what will happen is between -1 and 1, this graph will converge. Outside of -1, right, if I zoom out, you can see on the other side of -1, these graphs go in all different directions. And to the right of +1, you're not even in the same quadrant anymore. So there are places where this is a good approximation, and there are places where this is an awful, awful approximation. So coming back to this thing over here, if you want to now match up my graphs with the information that's presented here, we can say that this thing has an interval of convergence. And all of these terms we'll talk about a little bit more in depth as the chapter goes on. So an interval of convergence, in this case, goes between -1 and 1. All right, and as we go through the chapter, we'll talk a little bit more about, do I want to include the -1? Do I want to include the +1? Do I want to leave them both open, include one, include the other? But we can get to that. We've got time. All right, so what we just did is we made ourselves a power series. That green guy up at the top that we had talked about before, the sum of all the x to the n's, that is our series representation for 1 plus x squared plus x to the third plus x to the fourth, and so on. So let's spend a couple of minutes just writing out what is a power series. Okay. This power series, by the way, is centered at 0. How do I know it's centered at 0? Because at x equals 0, you notice everything comes together right there. As you go further to the right of 0 and further to the left of 0, these graphs start to separate from each other. But there at x equals 0, that's where they all come together. That is what we call the center of the series. Not every series is centered at x equals 0. For example, the natural log function would be a terrible function to center at x equals 0 because the natural log of 0 doesn't exist. So let's talk a little bit about definitions of a power series. So the first thing I'm going to do is I'm going to write out this, the sum from n equals 0 to infinity, and sometimes your textbook uses k's instead of n's. That's okay, we'll be all right. The sum of all the c sub n x to the n's looks like what? It looks like c sub 0, right, because x to the 0 is just 1, plus c sub 1 times x, plus c sub 2 times x squared, plus c sub 3 times x to the third, and this thing keeps going until I get to c sub n x to the n, and it keeps going past that, all right? Those c sub 0, c sub 1, c sub 2s, those are the coefficients. What are the coefficients? Well, it depends on the series. You tell me the series, and I can tell you what the coefficients are. This is a power series that's centered at x equals 0. Okay? We actually have a name for a power series centered at x equals 0. We call it a Maclaurin series. Okay, so if you ever hear the word Maclaurin series just means a power series that's centered at x equals 0. Like I said, not every series in the world will be centered at x equals 0, so the second formula is a more general form of that first formula. So the second formula looks like this. The sum from n equals 0 to infinity of all the c sub n x minus a to the n's looks like what? C sub 0 is the first term, right? And if I do an x minus a to the 0, I just get 1, so there's no need to write that out. The next one will be a c sub 1 times x minus a. The next one will be a c sub 2 x minus a squared. And this will go until I get to c sub n x minus a to the n, and keep going over that. That is a power series that's centered at x equals a. So, like my natural log function, I will not want to center that at x equals 0, but I might want to center that at x equals 1, and so I would use a power series formula that looks like that to talk about what happens to the series centered at x equals 1. All right, these power series can do one of three things. And again, we're going to do a lot more with this as the chapter goes on, but this is just some basic introductory stuff. So a power series will do one of these. Right, it's got three options. One of them is that it's going to converge on an interval. So it's going to converge on some finite interval. That, by the way, is what the example we just did. Right, this guy over here converged between -1 and 1. So it was a finite interval between -1 and 1. That's where the series converged. Outside of that, the series diverged. Okay. What else could it do? The other option, well, there's actually two other options. The other two options are it could converge for all x. You know that if I use that upside down a, that means for all. Okay, so it converges for all x, or it can converge only at the center. And so the second one, if you were to graph it, what you would see is just a bunch of lines, and the curves would end up on top of the function all the way through. Converging only at its center means that all those graphs would converge and hit only one point, and then outside of that one point that it's its center, then you would see all the graphs start to diverge. So those are the three options. Now, we can build our own power series as long as they're power series that are based in some way on 1 over 1 minus x. So let's try to create a power series for 1 over 1 plus x. All right, so let's take a look at an example. Create a series to represent 1 over 1 plus x. Now, what do I know? I know that 1 over 1 minus x equals 1 plus x squared plus x to the third plus x to the fourth, and so forth, right? That's 1 over 1 minus x. If I want to do 1 over 1 plus x, maybe I can think of 1 over 1 plus x as 1 over 1 minus a negative x, right? Isn't that 1 over 1 plus x? And then I can replace all those x's with a new ratio. So now instead of my ratio being x, now my ratio is negative x. So I'm going to take all those x's that I had, and I'm going to replace them with negative x's. That should be a third, negative x to the fourth, and so forth. Let's move this up for just a second and simplify. If I simplify the left-hand side, I'll get 1 over 1 plus x. On the right side, I'll get 1 minus x. Now, when I square the negative, I get a positive. So I get plus x squared, then I get minus x to the third, then I get plus x to the fourth. So this thing is alternating. Now, what does this look like in general? Can I write myself a general term? Because this part here, the 1 minus x plus x squared minus x to the third, that's the polynomial part. Suppose I want the general term. Right? The general term is the one with the n's in it. So this becomes, well, I can see that it's going to be some form of an x to the n. But I also need something to make it alternate. Now, if I put a negative in there, does that work? If I start this thing here at n equals 1, or if I start at n equals 0, n equals 0 would give me a 1 for the first term, n equals 1 would give me a negative x for the second, n equals 2 would give me a positive x squared. So it looks like if I write this series starting at n equals 0 to infinity of negative x to the n, that is the series, which, by the way, I could also write with the negative 1 to the n, right? I could write negative 1 to the n, x to the n. Just make sure when you do this that your series is doing what you really want it to do. So if you're trying to alternate terms, make sure the negative is on the inside and the power is on the outside. If you don't do that, then your series will not alternate the way you want it to. All right, so I've got the polynomial part, I've got the general term, and then this whole thing, if I keep carrying this out, is equal to the actual series of negative x to the n starting at 0 and going to infinity. And that's a polynomial representation for 1 over 1 plus x. In other words, what I've done is I've taken something that is clearly not a polynomial, right? 1 over 1 plus x, clearly not a polynomial, and I've turned it into something that is a polynomial. Right, what if I wanted to find the Taylor series representation or power series representation, let's keep words in order here, of x over 1 plus x? Well, if I take the red function, 1 over 1 plus x, and I multiply top and bottom, or multiply the top by x, then I'll end up with x over 1 plus x. So you can multiply every term of a Taylor polynomial by some constant or some variable, and it doesn't change the meaning. So if I take the red function, multiply everything through by x, now I get x minus x squared plus x to the third minus x to the fourth, and so forth. How do I write the general term for this? Well, now I still want the signs to alternate the same way, so I still want that negative 1 to the n. But if I take this x to the n over here and I multiply it by another x, then I'm going to have one more x than I had before. So instead of n of them, I'm going to have n plus 1 of them. So there's my general term. If I want the series representation for this, let's start the series at n equals 0 to infinity, negative 1 to the n, x to the n plus 1. So in this case, I can't get away with, like up here, I put the negative and the x together on the inside. I can't get away with that over here because now the two indexes are different, right? I need the alternating part to have a different power than the x. All right, let's take a look at one more of these, and then we'll start the derivation of the Taylor polynomial on a different video. So let's say I want to find a series for 1 over 1 minus 2x. Okay, so let's say I want a series for 1 over 1 minus 2x. This is really just an exercise in watching your parentheses. Again, I know what 1 over 1 minus x is, and this is something you should commit to memory. 1 plus x squared plus x to the third, and so forth. Okay. Instead of having an x, I'm going to replace the x's with two x's, right? So I'm going to put that 2x in parentheses for just a second. So 1 over 1 minus 2x is going to be 1 plus 2x plus 2x squared plus 2x to the third, and so forth. So what does that look like when I simplify it? 1 plus 2x. Now don't forget to square constants. I get a 4x squared. I get an 8x to the third, and so forth. If I want a general term, what does a general term look like? Well, this one's not bad, right? Because it's just the 2x as my ratio, and the n is my exponent. So that's my general term. If I want the series representation, go from n equals 0 to infinity, 2x to the n. Right? So 2x to the 0 is 1, 2x to the first, 2x to the second, and so forth. Making sure that you match up that index on the bottom with the exponent on the top, and that it matches up with your series is important so that you get the right terms in your series. Okay. So here's the hook for the next video. All this stuff that I've done up here has all been based on 1 over 1 minus x. But I'll bet you there's other functions that we want to find polynomials for besides just 1 over 1 minus x. There must be a way to figure it out in general, and that's what we're going to do next.